Today, I want to introduce our joint work on the unfairness of active users and popularity bias in point of interest recommendation with Hossein, Yashar, and Ali. A state-of-the-art point of interest recommender algorithms commonly uses historical data to provide personalized recommendation to users and help businesses attract potential customers. Recent study has suggested that such data-driven recommendation could be impacted by various biases that might exist in the data. Most existing research works in the fairness of recommender system treats user fairness and item fairness as two separate issues, disregarding that such system might work in a two-sided marketplace and there might be an interplay between these items. In this work, we have studied the interplay between personalization and unfairness, both on the side of users and producers. In particular, we have studied the interplay between unfairness of active users, unfairness of popular item, and accuracy of the system as three angles of our study, and try to answer three main research questions. First, to what extent are users or groups of users are interested in popular POIs? For this one, we have tried to identify what is the natural data bias toward popularity. Then we answer, is there a trade-off among the factors of accuracy, user fairness, and item fairness, and whether we can classify algorithms based on their performance on these three criteria. To this purpose, we use two famous real-world POI datasets for our study, namely Yelp and Gowalla. As you can see, both of these datasets are extremely sparse, which makes them more likely to be affected by various data biases, and that motivates us to choose POI domain for our study. However, our finding and insight should be trivially extendable to other domains as well. For the train test scenario, we use a temporal split with 70% of the oldest check-ins as the training data, then the 20% of the most recent check-ins as the test data, and the remaining 10% as the validation. Okay, so now the first research question. To what extent are users or groups of users interested in popular POIs? To this purpose, we analyze the user profiles regarding their check-in behavior. As you can see in graph A and C, we see a long-tail distribution of items where few POIs are visited by many users, while other POIs are visited rarely or by only few users. These popular POIs consisting less than 10% of the total catalog size. In graph B and D, we plotted the ratio of popular POIs that users are visited. As you can see, they show that in both datasets, there are more than 85% of users that have at least 20% unpopular items in their profile. To analyze the quality of recommendation algorithm in propagating these biases on different types of users and items, we divided them into a few categories. For items, we sorted items based on their popularity score, based on the number of check-ins, into three groups of long tail, mid tail, and short tail, where the 20% of the highly popular items are in the long tail of our distribution, 30% in the mid tail, and the remaining 50% in the short head of this distribution. For the user groups, following the literature cited below, we divided users into groups of very inactive, slightly inactive, slightly active, and very active based on their number of check-ins that they had in the system, in their user profile. We also calculated the correlation plots between user profile size and popularity of items. As you can see, there is a positive correlation between the number of popular POIs in the user profile size, in the user profile over the profile size. That means that the higher is user's profile, the higher the user interact with the system, the more chance there is that the user interact with popular items. However, when we plotted the user profile size versus the average popularity of POIs, we notice a downward trend, a negative correlation. which suggesting that users who are actually more active and contributing most to the system are interested into more unpopular items rather than popular items. The next research question we try to address is we want to answer whether there exists a trade-off among the factors of accuracy, user fairness, and item fairness, and whether we can classify algorithms based on these metrics. To this purpose, we first need to define how to measure and evaluate each of these aspects. For evaluating accuracy, we use normalized discounted cumulative gain, or NDCG, to measure fairness between user and item groups. We use two metrics of GCE and MADRR. Mean absolute deviation of ranking performance, or MADR, is capable of to compare the difference between ranking performance among two groups. That is, it is capable of measuring the disparity between two different user or item groups. Generalized cross entropy, on the other hand, is a flexible evaluation approach that is capable of comparing the distance between two distributions. So PF here stands for the ideal fair distribution, where uniform or parity could be just a special case of it, while PM is the actual recommendation distribution. So GCE is capable of measuring the distance between these two distributions as a criteria of fairness. We further chose several state-of-the-art recommendation algorithms to study this interplay in them. In the conventional models, we chose MOSPOP, BPR, WMF, and PF, and we also included two neural collaborative filtering models, neural matrix factorization and variational autoencoder collaborative filtering, to compare the difference between conventional and neural-based models. We also included two state-of-the-art context-aware algorithms, so the effect of domain-specific contextual information gets investigated in this interplay as well. These two models are GeoSoka and LoRe, which are two popular models in POI recommendation. In this slide, we analyze the relationship between three evaluation objectives, that is accuracy, user fairness, and item fairness, with three 2D plots. The ideal representation for the algorithms would happen at the top right corner of each of these plots. This indicates the better performance in accuracy and fairness. So the higher are the values of user fairness, item fairness, and accuracy, the better it is for that recommendation algorithm. As you can see, the majority of algorithms do not reside in the top right corner of the plots. This implies the existence of a trade-off between the accuracy and fairness of recommendation models. For example, look at LoRe models, the pink square model in the picture. LoRe sacrifices user fairness to achieve a very good level of item fairness and accuracy in Gowalla dataset. Also, we can see that weighted matrix factorization achieves comparable performance on both accuracy and user fairness, but they suffer seriously from producer fairness, the item fairness. A plausible explanation for these trade-offs lies in the data biases themselves. In this table, we are measuring the performance of our three criteria that we described in more detail with numbers. PF shows different ideal representation of fairness among user and item groups, in which PF0 shows that quality of recommendation is distributed relatively evenly among user or item groups, while other PFs, PF1 to PF4, shows the skewness towards a particular group. So for example, PF2 shows whether our recommendation system is skewed toward group 2. To measure the interplay, we also computed area under curve of our 2D plots to capture the 2D interplay between these factors. Our result shows that among all models, VAECF overall achieves the best result among other models on both data sets on accuracy, while also keeping a reasonable amount of user and item fairness, and as can be seen by the values of AUCs in this table. We also noticed that Poisson factorization using the Poisson distribution can capture the long-tail user activity found in most consumption data and model the relation between users and items on implicit feedback dataset in a better way. The observation on item fairness also shows that all methods have the lowest value of GCE in an absolute sense under the PF1 column. This means that popular items receive higher exposure opportunities in all algorithms experimented in this study. However, between all models, contextual-based models, which would be Lore and Geosoka, overall improve item fairness on both datasets. This indicates that the impact of contextual influence on POI recommendation can provide a diversity of items in the recommendation list. To conclude, we analyzed the trade-off between accuracy, relevance to user groups, and popular item exposure fairness. We also noticed that numerous methods fail to balance the item and user fairness due to natural biases in the data. VAECF model produces the best level of accuracy, user fairness, and item fairness in comparison to all models experimented in this work. We also noticed that usually one aspect, either item fairness or user fairness, is compromised to keep the accuracy high. In other words, models that had reasonable amount of accuracy were suffering from either item fairness or user fairness issues, or both. As future works, we think it would be interesting to extend the experiment on more data sets from different domains and models to verify whether this result holds for other domains and data sets as well. Furthermore, investigating the different type of biases, such as gender bias, can be also a potential future direction. There might be a correlation or a trade-off between gender bias and other biases that exist in the system. Furthermore, proposing a single metric that can serve for the evaluation of all dimensions that are important for a recommender system model can be very beneficial so that researchers can focus on optimizing that metric without being worried about the various interpolation and trade-offs that might happen between the evaluation metrics. And finally, our result codes datasets are all available on GitHub, and you can follow this link for more information about all our experiments. Thank you, everyone.